Okay, time for section 1.2, initial value problems. This is basically finding the constant. So I don't remember if you remember last time, right here at the end, this last example, we had a solution that involved a constant c, right? Some real number. And essentially what initial value problems do is allow you to pin down this constant, right? You have to set some boundary conditions or some initial conditions on the function, and then it pins down a constant. So here's the setup. We have a nth order differential equation, right? We're going to put the nth derivative term on the left-hand side by itself with a 1 out front. I mean, it doesn't really matter how you write it, to be honest. This is just the general form of an nth order equation. The exact form doesn't matter. And then on the right-hand side, we have x and the other n-1 derivatives of y. The important part about an initial value problem is this keyword phrase right here, such that, or subject to. That indicates to us that this is going to be an initial value. Like following this statement comes a set of initial values. And you always have n many initial values if you have an nth order differential equation. So the order of the differential equation is n. We're going to have n many initial values. I know it may seem that there's only n-1, but we start at 0. So really there is exactly n many initial values. And these y0 to yn-1s are called the initial values. And I forget what people call the x0 number, but it is all the functions y are evaluated at the same point, right? So if you want to think about this graphically, we have some function y, and then there's some point here x0, right? And you're specifying the height of the function at this point, that's this value. You're specifying the slope of the function at this point, that's this value. And then there's not really a good interpretation of the higher order derivatives, but you're specifying those as well. So you have this singled out point x0, and you're specifying the behavior of the function at this point x0. This type of problem is called an nth order initial value problem, and the specified values after the such that or the subject to are called the initial conditions. Here's an example. Let's consider the one parameter family of solutions y equals 1 over x squared plus c. 1 over x squared plus c. So there's this constant c floating around in our solution. These infinitely many functions, right? There are infinitely many functions for each value of c. Excuse me, I said that wrong. There are infinitely many choices for c, and each one of those gives you a function that's a solution to this differential equation. And our challenge is we want to find a particular solution to this equation with the largest interval I, for which we pass through the point 0, 1. This is a first order differential equation, right? There's only one, the highest derivative here is 1. And so we only need one initial condition. Well, if we have to pass through the point 0, 1, we already know what the solutions look like. So we know that if this must pass through the point 0, 1, we can just plug in 0 for x and 1. Sorry, negative 1. I've been saying 1. Negative 1 for y, right? Since we know that this is a solution, we can just plug in this pair of points to evaluate c. And when you do that, you find out that c equals negative 1. Therefore, the solution to this initial value problem is y equals 1 over x squared minus 1. And the question is, what's the interval I for which this thing is defined? Well, we just need to draw the graph of this function, right? This is how the function looks. If you forgot how to graph rational functions, you should probably go look that up. This is a rational function. We know that the zeros of the denominator give us these vertical asymptotes at plus and minus 1. That's where I got these. And then the behavior in the middle is determined by you just plug in some values in between those points. So like if you plug in x equals 0, you see you get y equals -1. If you plug in x equals 2, you get, what do you get? 1/3, which is a positive number. If you plug in x equals -2, you get 1/3, which is a positive number. And you can kind of see how the shape of the graph is. Now, one thing I didn't mention is that we need to pick an interval I where the solution is continuous and differentiable, right? And since this is a piecewise function, more or less, right, it has vertical discontinuities, right? I guess you'd call these asymptotic discontinuities. We have to pick the largest interval I where our solution is differentiable and our solution passes through the initial point. It's not too hard to see that this is the largest section we can take, right? This is the largest piece of the function that's differentiable and passes through the initial point, 0, -1. Overall, we have 3 options for what the interval could be, right? We could pick this interval, which is this interval here. We could pick the middle interval or the right-hand side interval, and the only one containing the initial point is this middle interval. Therefore, the solution to the initial value problem is y equals 1/x² - 1 on the interval -1 to 1. Okay, same differential equation, same family of solutions. Let's change the initial value. So now the initial value is going to be that y of 2 is equal to 1/3. So again, we can just plug in x equals 2 and y equals 1/3 into y, the expression for y, to find what c should be equal to, right? So in this case, c should be equal to -1. We get the same graph, right? The same graph as before. But now we want to take the interval where 2, 1/3 exists. And in that case, it's the interval from 1 up to positive infinity. So now that we've changed the initial condition, we get the same solution, but the interval of definition has changed. And then if we try a different initial condition, say y of 0 equals 1, then plugging in x equals 0 and y equals 1 into this equation tells us that c should be positive 1. And in this case, we get the solution y equals 1/x² + 1. And if you don't know how to graph this, you should go look up how to graph a rational function again. They're going to be showing up a lot. But the short story is that the graph looks like this, right? This is the graph. And since this is differentiable everywhere, we can take the entire real line as the interval of definition for this solution. Okay, here's another problem. So they're telling us that x equals, okay, so in this case, something I should mention is that it's totally possible that x is the dependent variable, right? In this case, we're thinking about x as a function of t being a solution to some differential equation. This actually comes up a lot in physics, right? When you have something moving through time and x is the position variable usually. So now we have a two-parameter family of solutions. X equals C1 cosine 4t plus C2 sine 4t. This is going to be a two-parameter family of solutions to the following differential equation. X double prime plus 16x equals 0. If you're uncomfortable with x being the dependent variable, you can totally make the transformation. X goes to y, t goes to x, and like just pretend that x is y and t is x, and then you'll be in the case of looking for an equation y of x. But it doesn't hurt to swap the variable labels around, right? We know that it doesn't really change anything, but it's good to get acquainted with other variable labels, other labels for the independent and dependent variables. Since this is a second order differential equation, I'm going to need two initial conditions, right? Two initial conditions to pin down a specific solution. That's also pretty easy to see because we have two unknowns in our general solution. And how do you solve for two unknowns? You need two equations, right? Two equations to solve for two unknowns. Each one of these initial conditions is going to give me an equation. And once I have those two equations, I can solve for the two unknowns. Sometimes it's easier than that. Sometimes one of these will immediately give you one of the constants, and then the other one will be obviously going to give you the second constant. Okay, let's see what happens. So we take our general solution to the differential equation, and we're just going to evaluate this first condition, right? So we're going to plug in t equals pi on 2 and x equals -2 into our solution. Okay, evaluating that. X equals -2, C1, cosine of 4t, t becomes pi on 2, plus C2 sine 4, and t becomes pi on 2. So we've got -2 equals C1 cosine of 2 pi plus C2 sine of 2 pi. And we know that the sine of 2 pi is 0, and the cosine of 2 pi is 1. So we get -2 equals C1. C1 equals -2. Given that information, we can now use this second initial condition. But you'll notice that this is a condition on the first derivative of x, right? This was a condition on x, but this is a condition on the first derivative of x. In order to evaluate this initial condition, we have to take a derivative of our solution and then plug in for t and x after we take a derivative. So step one to evaluate this initial condition is we're going to take our solution, our general solution, and we're going to differentiate it dt. Right, so a derivative of this dt. X becomes x prime. C1 is a constant, it's hanging out. The derivative of cosine 4t is, derivative of cosine is negative sine. Keep the 4t, and then you chain rule the 4, right? So the outside function here is cosine, right? The outside function is cosine, and the inside function is 4t. So when you take a derivative of a function, you take derivative of the outside, keep the inside, times the derivative of the inside. Okay, same thing on the second term. C2 is a constant, it's hanging out. We've got sine of 4t, which is a function of t. So to take the derivative of sine 4t, we take the derivative of sine, which is cosine, keep the inside, times the derivative of the inside. And then cleaning up a little bit, we get to here. And then we can plug in for, what is it? X equals 1 and t equals pi on 2 into x prime. 1 equals -4c1 sine of 2 pi plus 4c2 cosine of 2 pi. This term is 0, Sine of 2 pi is 0. This term is 1, so we get 1 equals 4c2. And solving for c2 means we just divide by 4 on both sides, right? And we get c2 equals a quarter. So we've got c2 equals a quarter, c1 equals negative 2, and we know that the general form of x, we can find the specific solution satisfying these initial conditions, which is x equals negative 2 cosine 4t plus 1/4 sine 4t. And since these functions are defined everywhere, they're nice and continuous and differentiable everywhere, the solution is on the entire real line. Here's the basic solution of, this is the most of the theorems in differential equations are of this flavor. I call them existence and uniqueness theorems. They basically say that a solution exists and it's unique under these conditions. So let's read this one. It says, if you have a differential equation, that's a first order equation, subject to a excuse me, an initial condition. So you have a first order differential equation and an initial condition. And you need to have some rectangular region in the xy plane defined by x is between a and b, y is between c and d, that contains this point x naught, y naught. Right, so we're thinking about this point x naught, y naught being in the plane, and then we need some rectangular region around that. If this function on the left-hand side, f of x and y, and its partial derivative with respect to y are continuous on this rectangle, then there exists some interval I around x naught contained in our rectangle, and a unique function y of x defined on this interval. That's a solution to the initial value problem. It's very wordy, I understand. Here's a little picture, maybe this will help. The idea is you have some point x naught, y naught. You have the point up here x naught, y naught in the plane. You have this rectangular region R defined by x between a and b, y between c and d. It says as long as these conditions about f of x and y are met, right? Like smoothness conditions on that function, then a solution exists on a small interval around x naught. Could be bigger, but it just guarantees the existence of a solution on some interval. Let's see if we can play the game and figure out what's going on. Here's an example. Determine a region of the xy plane for which this function would have a unique solution. So this guy right here on the right hand side is our f of x and y. Right, this is our function of x and y. The conditions say that this function and its derivative dy have to be continuous on a rectangle. Well, this guy is continuous so long as y is greater than or equal to 0. Right? If y is negative, we get bad stuff happening since we're dealing with real value functions here. So as long as y is greater than or equal to 0, this guy is continuous. And if we take partial derivative of f dy, if you don't remember how to take a derivative of a square root, you have to remember that this is actually like y to the 1/2 power. And then you can just power rule this guy when you take a derivative. The 1/2 comes down, you subtract 1 from the power, you get y to the negative 1/2. This is continuous as long as y is strictly bigger than 0, right? If you put y equals 0 in the bottom here, you'll be dividing by 0. That's not good. So we have to have strictly larger than 0. Therefore, as long as y is greater than or equal to 0 and y is greater than 0, this differential equation will have a unique solution. That's the only condition on my initial point, x comma y. So in this case, the rectangle R that we're looking for in the theorem is this upper half plane, which spans the entire length of the axis, does not equal the axis, and everything above that. This is not really an important concept to have down, but it's the basis of every uniqueness theorem that's going to come later. Okay.